Welcome to the Cummins Power Hour webinar series, the program designed for our engineering partners like you. The program offers concise technical presentations on topics pertaining to on-site power system design and specification. The program aims to keep you updated on products, technology, and codes and standards development, the topics most relevant to the jobs and projects you are working on. You can earn one professional development hour issued by Cummins upon your completion of today's webinar. This webinar will be recorded and archived. If you missed a webinar or want to visit our archive of content, please visit our on-demand webinar center and replay any topic at your convenience. We have muted the conference line to ensure a quality sound environment during today's presentation. If you do experience any challenges with the audio broadcast during today's Power Hour, please navigate to the audio button on the bottom left of your Zoom application to ensure your device is connected and test your device if needed. Throughout today's Power Hour, you are encouraged to ask your questions as they come to you. Our expert panelists will do their best to address questions through text answers during the presentation and verbally in the Q&A session at the end of today's Power Hour. Also, at times, our speaker may pose questions to you. If we ask you a multiple choice question, we will prompt a poll that will appear through your Zoom application. For open-ended questions, however, we encourage you to click that chat button to engage with our speakers and panelists. We would love seeing your engagement to all of our questions. My name is Michael Sanford, Product Strategy and Sales Enablement Leader for Cummins, and I will be your host today. We are excited to bring you the topic, Considerations for Generator Set Selection. The presenter for this session is Mark Taylor, Technical Advisor from the Technical Marketing Team. For the Q&A session, we also have two special guests, Bob Kelly, your local Senior Application Engineer for Florida, and Dennis Tarr, your local Senior Application Engineer for Washington, Oregon, and Alaska. We have a great topic for us today and are looking forward to any questions that you may have. With that, I'll turn it over to Mark.
All right. Thank you so much, Mike, for that awesome introduction. So I will go ahead and kick things off with our usual boilerplate disclaimer. I am here to give you a great and thorough and comprehensive education on, well, considering how to select a generator set and size and select that generator set. I will be touching a little bit on NEC, NFPA, a couple other codes. Just to let you know, anytime I talk about these codes, I am not an AHJ. That being said, this is a good faith interpretation based on our experience working with these codes and AHJs on a regular basis. But the final authority, of course, will always lie with your local AHJ. So refer to us if you would like any help with any conversations in the future. So design in engineering is frequently an exercise in optimization. Optimization of price versus performance, features between different manufacturers, being efficient with the design versus being flexible for possible future changes in customer preferences, for example, you name it. Engineers are frequently a jack of all trades with a need to understand the perspectives of numerous stakeholders. And in the world of selecting the best generator set for your customers' needs, things are no different. In this course, the aim is to take a step back and outline the most important key questions to ask first, even before knowing the types of loads that the customer is trying to serve. We will then go through the basics of generator set sizing to an overall set of loads with a quick overview of generator set derates as a function of altitude and ambient temperature. We'll then continue to drive into more specifics as the course goes on. We will wrap up with the fundamentals of load application, transient response, the key strategies for optimizing your inputs in a generator set sizing software. We'll offer plenty of additional resources for you along the way. So if you want to dive deeper into a host of different topics, we'll get you set up with information for you to reference later. So to set the stage of this conversation, let's first outline the most important points of communication through the design process. What we have here on the left are the manufacturer's products, and inherent to those products are the features and the capabilities that set them apart from one another, of course. On the right, we have your customer's design requirements for your next project, whatever that project may be. For this presentation, however, we're going to keep things relatively simple by assuming that for most of you all, we're going to be talking about standby for emergency use loads. I intentionally have a big gap here because there's so much work that happens in between meeting those requirements with the performance of those products. So at the risk of oversimplifying, and not to downplay the immense amount of work that goes into bridging the gap between product capabilities and customer requirements, I'll offer two of the key components used in the communication between these two sides, being the specification language, best used to communicate the requirements of the power system, and the submittal response to that specification, outlining the features and capabilities of the product to demonstrate its compliance to said requirements. Included in the submittal may be generic items such as outline drawings and data sheets, but also integral to that submittal is usually a sizing report with the manufacturer's sizing software, showing that the generator is the best fit for the job. What we'll spend most of this presentation outlining is an understanding of that sizing. So let's get the big stuff out of the way first, which actually leads me to my first question to you all. So go ahead and fire up that chat button as we explained earlier. My question to you, what are some of the earliest decision points when approaching a new system design, even before reaching for that sample specification? So I'm seeing fuel a handful of times, picking the fuel choice. Just how big of a job is this? What kind of, the codes that are behind the loads that are being served? Tell me about the loads, diesel versus gas, inside or outside, load types. Let's see here, lots of really good answers. Diesel versus gas, emergency versus legally required versus optional. Just give me a load study. Wow, I can't even take a time to go through all these, but you guys have nailed it basically. Elevation, voltage, environment around the generator set. Love these answers. Thank you so much for engaging. I'm going to go ahead and put a pin on that. Thank you so much for engaging with it. Emissions requirements, just at the nick of time. Yes. All right, I'm going to move forward. Thank you so much once again. So one of the very first items that comes to mind that I usually hear are questions regarding the generator set rating. What are they? How do they differ? Why do manufacturers seem to have slight tweaks or variations on some of these ratings? Does one preclude meeting EPA emissions requirements, for example? I've heard so many questions about ratings and their definitions in my years at Cummins, so this is a great place to start. It is important to note that generator set duty ratings are primarily based on a standard ISO 8528-1. That being said, ISO 8528 is a reference standard. It's not a law, it's not a regulation, and we'll get back to that in just a moment. Generator set ratings basically are describing two variables: whether or not the load profile is constant or variable and fluctuating, and secondly, a general expectation of annual run hours. Let's first walk through the most common examples of ratings that are outlined in this standard. So the first one, emergency standby power, that's why I mentioned at the start of this presentation. That's what most of everyone in this call is specifying around. It's intended to back up a reliable utility. So the load profile, because you're in a blackout situation, is going to be variable because the loads of that building, for example, if it's a standby generator for a building, they're obviously going to be variable as fire pumps come on or as elevators are used or not used. And generally speaking, because it's a standby unit, there is a number that ISO 8528 suggests. They throw out 200 hours. Moving on to another very common rating that you may have heard before is prime. The key difference between standby and prime in their rating is prime will have an unlimited runtime. This is best served for a remote mine site, for example. If a same, in Cummins, we'll have one generator that serves loads of that could be prime or standby, and usually the only difference between the two is the prime generator will just have a slightly lower power rating to it. So we can ensure that it'll definitely last for 8,760 hours a year. So I'm not even going to go to the details of all the rest, but these are the ratings that ISO 8528 describes. So now that I've gotten the greatest hits of the definitions out of the way, I'd like to clarify on one main point that I just alluded to earlier. Most of you, I'm sure, are based in the United States or Canada, and I am frequently asked about the implications that max run hour statement of 200 years I just mentioned. This is, for all intents and purposes, a good faith estimate, but it's not a rule. This standard is international, just to take a step back into context. So not every region of the world has as reliable utility power as we are used to in the United States and North America. And so this good faith estimate is intended to kind of separate out standby gensets for otherwise reliable utilities and gensets that are likely should go to prime, honestly, with the utilities that are comparatively have more downtime. So to keep things simple, if you're a standby application in the United States, you're most likely going to be asking for a standby generator set. So what to specify? ISO 8528 is a reference standard. All reputable generator set manufacturers at least meet this standard. So ask for it that way. My key recommendation to you is ensure that your call out to duty rating is clearly defined in your specifications. It could be as simple as punting to ISO 8528 or working with your manufacturer to get the right definition for you if there's ever any doubt. The next key decision point that comes to my mind is the physical location. And I know a number of you cited this in the chat, the physical location and surroundings of the generator set. There is so much potential variety at play here, and I can't enumerate all the differences to the finest detail. But one of the biggest drivers of key specifiable differences is whether the generator set will be installed out of doors in an enclosure or indoors in its own dedicated facility. One is not inherently better than the other, but each method has its own set of positives and key watchouts to work with. Generally speaking, enclosed units outside are about as close to off the shelf as a generator can get. They will come with their own hardware, such as mufflers, or even can come with a variety of diesel fuel tank options if it's a diesel generator set, of course. The potential drawbacks of an enclosed generator can be that outdoor real estate that is needed can just simply not be in the cards. And as gorgeous as I think these products are, some customers may tend to disagree, and they would rather tuck these products in back or side lots that may have strict noise requirements with next door neighbors. So looking at the indoor installation on the right, this approach can be a great option, but may come with the added complications of keeping the generator set cool with adequate airflow or keeping noise and vibrations from transmitting within the building with proper isolation. So of course, I said there are many considerations at play here, but I cannot go into each and every one of them. I recommend for further reading our T030 application manual, our complete and unbiased approach to best practices in mechanical and electrical design in and around generator sets and power systems, both indoor and outdoor. Also, I mentioned sound and acoustic concerns. We have an excellent recording of a previous power hour on this subject, and I'll leave you with a link on that so you can click on this on your own time. When you do get a copy of this presentation, within the next handful of business days following this event, all of these blue links should be clickable for you to bring you to those resource materials. Another one of the earliest decision points needed to be made, and a number of you pick this one up as well, before picking up a generator set specification includes the selection of fuel type. Typically in the space of emergency standby use, the choice is between diesel or natural gas as a fuel source. I cannot stand making broad generalizations, but here I am doing it anyway. But I just wanted to make an important point though. There exists a lot of old notions and misconceptions about the capabilities of gaseous fuel generator sets, and I highly encourage you to give them a fair shot or another look if it's been a while. I want to challenge the thought that gas generators cannot start in time for NFPA 110 Type 10 compliance. Our largest generator set that can meet those requirements is 1.3 megawatts. Cummins knows that customers and end users see a lot of appeal in not having to maintain diesel fuel, which requires vigilance with regard to fuel levels and fuel quality inspections. Gas, comparatively speaking, for fuel is lower maintenance. And if I may reinforce one other point about diesel and gaseous fuel generator sets, there is usually a consternation in and around the applicability of solely relying on the utility gas feed for life safety loads. With an on-site source of fuel with automatic changeover with propane, for example, a gaseous generator set can check all the same boxes as a diesel generator set in the eyes of the varying articles of the NEC, while still being more convenient than diesel due to the near infinite life of propane. The only time a utility-only source of gas is forbidden is with the strictest article of the NEC 708 for critical operations power systems. Even for Article 700 life safety loads, utility-only gaseous fueled generator sets are sufficient so long as the local AHJ allows it. And just in case these articles of the NEC are unfamiliar to you, we'll be discussing them later in a bit more detail, and I'll offer examples and definitions for you then. Oh, I think I skipped one thing. I wanted to call out this one other related source of information. Of course, we have a much more in-depth power hour. We dedicated a whole hour to just diesel as compared to gaseous generator sets. I highly recommend clicking that link and checking it out. I'll end this section on key early decisions with meeting your local or federally mandated emissions requirements. Fun stuff. Emissions requirements can have a big impact on the products available for your power system. And the rules around emissions revolve around the fuel type and the usage of that generator set. In the US, the federal level of requirements are set by the EPA's new source performance standards. Again, trying to maintain today's focus for standby emergency operation. This application is one where the engine-driven generator set is used as a backup to a primary source of reliable utility power. And these would fall under the EPA's stationary emergency designation. The EPA, frankly, doesn't really care what duty cycle generator set that was purchased. So theoretically, you can purchase a prime or a data center continuous generator per ISO 8528 or for the manufacturer's ratings definitions. But so long as it is being used as a backup of an ordinarily reliable utility, it will still be categorized as stationary emergency usage. The federal level establishes a baseline level of requirements, but any local or state air board can exceed those requirements. It is tough to fit local air requirements into nicely named categories like the EPA's regulations, but simply just be aware that the local air board has the authority to regulate each emissions constituent above and beyond the EPA levels. Again, this merits its own power hour, and we've already got you taken care of here. And so I definitely encourage you to check out this if you're interested in learning more about emissions requirements, especially meeting the particularities of local emissions requirements. So this brings us to our next concept check to kick off our next section. So I'm going to pose a question to you, and I'd like to see what your first gut check answer is, and try not to overthink this situation. If your customer comes up to you and says, I have about 350 kilowatts worth of load, what size generator set would you first think of to propose an answer? And I have a range of options here, and I also have I don't even dare want to answer option. So let me know your thoughts.
And Mark, as before, the answers are flying in here. There's a lot of folks answering B and C, and then a fair amount selecting that last option as well.
Mm-hmm. Yep. There's no shame in saying I'm not going to say yet, but I really like this question because it kind of gives a feel for just sizing to a generator set overall. So let's go ahead and end the poll and show the answers. It looks like it was nearly neck and neck between 400 and 500 kilowatts, with 500 just eking out 400 by, it looks like, by just a small handful of votes. Thank you so much for engaging with that. So let's dive in a little deeper about why I asked this question, because this next section is all about sizing to an overall set of loads. So I'm slowly getting more specific as we go through on this power hour. So to answer the question in the most generic terms available, I'll first refer back to ISO 8528. I didn't mention this before when I mentioned variable load profiles that are expected of a standby use generator set. But right there in the description of variable loads in ISO 8528, it goes into more detail about quantifying that variation in the loads. Of course, when you take a second to think about it, the peak load of a generator set cannot be higher than the nameplate rating of the product. That nameplate rating is the ceiling, if you will. So if you have a load profile that is going to have peaks and valleys, and if those peaks can be no higher than the generator set nameplate, then it stands to reason that the average load profile will be somewhere below the nameplate rating. The guidance from ISO 8528 offers 70% of the generator set nameplate to be the norm, and we find this to be a good guidance because it acknowledges the practicality of other sizing considerations that we'll get to later in this presentation. So how to specify around that? Well, if you use the same language that I suggested earlier, then you're well covered. And because when you call out ISO 8528, that's already baked in by making sure that your definition of standby in your specification says at least meet ISO 8528. That way, you're already covered with the load profile there. Of course, there exists one potential source of deviation from a generator set's posted nameplate rating, and that is the potential impact of altitude and temperature on its capability. This tends to go by the name of derate, and this is a phenomena that I'm sure those of you in the Rocky Mountains or in high temperature climates have heard of before. To offer a quick primer on derates and their potential impact on a generator set's power output, it's important to break things out into a generator set's big individual components. So first and most notably is the engine. Boiled down to its simplest terms, a reciprocating engine ingests air and fuel, combusts that mixture in such a manner to capture that chemical energy of the fuel and to convert it into mechanical energy of a spinning shaft. The most important ingredient in air for combustion is oxygen, and with less oxygen in the air at higher altitudes, an engine may reach the point where it cannot pull the same amount of power as it otherwise would have if placed at sea level. Just as each of us has a different lung capacity and breathing rate, the air intake system, including the turbochargers of an engine, have physical limits as well. Secondly, the next key ingredient is the alternator. Alternators may also be impacted by high altitudes or high temperatures, but for different reasons. Alternators need to be cool. They need to cool their windings. You may not see it as it's hidden in this picture, obviously, but alternators have a fan that draws air from the inlet nose on the left side of this picture through the internal windings to cool the rotor and stator. The hotter the air or the less dense the air due to altitude, the harder it gets to cool the system. Also of note, less dense air begins to start posing the risk of corona discharge with higher voltage applications, but I'm not even going to touch that animal in this course. Lastly, the cooling system that cools the engine through pushing air with that big fan you see on the right side of this image may also have challenges due to high temperatures and high altitudes for the same reasons as the alternator. Hotter and higher altitude air just simply makes it harder to cool the system. So with all that being said, I share all of this not to make you worry about all these details, but for your own awareness to help you keep the submittal response to your specification honest. If you've ever run through sizing software and saw numerous entries for a single generator set model, usually that's because the sizing software is offering different models of cooling systems or different models of alternators for your consideration as well. So to sum it up for you, Keep specifying the known environmental conditions, including the design temperature and the site altitude. Leave it to the manufacturer to provide for you the best fit equipment for the customer's needs. And let the awareness I provided allow you to ask pointed questions if necessary. Keep in mind, emphasis on the word ambient. Ambient temperature shall be measured at the air inlet to the engine generator for enclosed units, or at the room inlet for machines installed in indoor equipment rooms. So what I'm going to do here is check in on your votes. I'm going to launch this poll one more time and see how the answers may have changed, or if you're more confident one way or the other. So let's just ask that exact same question one more time. Again, assuming around, nothing tricky, no need to overthink it, low altitude, normal temperatures, and the answers are pouring in. So that tells me that there was a lot of confidence there. I'm pretty impressed with how fast that bar just snapped up. Should we go ahead and end it and share, Mike? Look at that. So before 400 and 500 were neck and neck, and you all by a large margin picked 500. And yeah, every site's different, every situation is different. For simplicity's sake, I would say, yeah, 500 is a great starting point, just to give someone a ballpark, what size generator set do I need for 350 kilowatts of loads. So I'm excited to see that shift happened. Thank you so much once again for engaging with that. It's always fun to see how things are going or playing out. All right, so we're going to move on to the next section. Now that we've covered the big early decisions and the high level overview of general sizing in the most general sense of word, now let's start talking about individual loads. So to kick things off, we're going to have a good old review of the importance of power factor. Power factor is the ratio of real power measured in watts versus the apparent power measured in volt amps. Breaking down the individual legs of this alternating current power triangle I have shown here. The vertical vector is the active or real power. Let us say, for example, we were simply consuming all electricity with a resistive load bank to just make heat. That would be an example of a load that is best described in watts, as the demands of the generator will be free of any magnetic fields for the most part. The horizontal vector brings us to the other leg of the triangle, volt amps reactive, aka VARS. VARS is the measure for power that is dedicated to the creation and the reduction of magnetic fields or electrostatic fields. The best examples of a more purely VAR heavy load would be an electromagnet or a motor before it starts spinning. The power in those applications is working to create and maintain a magnetic field. The resultant of these two vectors is the apparent power in volt amps. Once again, power factor is the ratio of kilowatts, the real power, divided by the volt amps, the apparent power. So one further detail about reactive power requirements. Those loads come in two main forms, inductive loads and capacitive loads. Inductive loads consume reactive power. Inductive resistance resists the change of current, causing the circuit current to lag the voltage. Examples of devices that produce inductive loads will include motors and transformers. Capacitive loads, on the other hand, charge and release energy, causing the current to lead the voltage, just the opposite of an inductive load. Many forms of capacitance can simply be inherent in a system and not be deliberately installed. But this brings me to my final point here. In a more realistic application, we will have loads that require a bit of both real active power and magnetic reactive power. The reason these details matter is that a generator set is not nearly as strong as the utility, and the loads being served are not nearly as diverse as the loads the utility is serving. We need to be vigilant to ensure the power system being designed remains in the sweet spot when it comes to power factor. And that is generally between 0.8 lagging on the right side of this image here and unity 1.0. power factor. There, we are making the most efficient use of fuel, that is to produce wattage to actually drive a shaft of a motor, for example, than using it to create magnetic fields. So overlaying that same power triangle, just shrinking it down a little bit and putting it over this typical alternator reactive power capability curve. And if you haven't seen one of these before, I'll walk you through it. We can best outline the ramifications of straying too far outside of that sweet spot I just mentioned. Too far into the right side, where loads are too heavily inductive, we may see diminished power system performance as we are burning fuel to just merely create magnetic fields, as opposed to doing some real work like driving a shaft. Now, understandably, when a motor is first starting, the power factor will be here for a moment. But if all steady state loads remain in that region, we may be running a bit hot in the alternator side of things. On the left side, if the loads are exceptionally capacitive overall, we run into the challenge of the current leading the voltage, causing issues with the alternator of the generator set being able to maintain control within the abilities of the automatic voltage regulator, or AVR. So ultimately, that primer on leading and lagging power factors leads us to this watch out for your consideration. Be mindful of the overall system power factor and absolutely consult your generator set manufacturer if you have any concerns. We can work with you to provide a gut check if the alternator selected can handle the job or not. I touched on this in the prior slide, but I'll go into more detail here. To reiterate, a generator set is not infinitely strong like the utility, and individual loads, as they are applied, will have an impact on the generator set response to those loads. The best way to explain a generator set response to an application of load is with an analysis of the transient response. Imagine you're driving down a highway on a flat grade at constant speed on cruise control. Now you suddenly hit a steep hill. How does your car respond? It'll probably start fueling more. It may even shift gears in the transmission to try to maintain that speed, but the engine has responded to that phenomena. That's an example of transient response. And I'm sure you all are well aware of different engine sizes in a small economy car or a large truck or SUV may respond differently to that exact same situation. The same analogy basically applies to generator sets in terms of picking the right size engine or generator to fit your needs. So what, generally speaking, frequency response is a great indicator on how well sized the engine is to the load, because after all, the engine is creating the wattage or the real power being consumed. The voltage response is a great indicator of how well sized the alternator is to the load, as the alternator is working to support the kVARs. So ultimately, there is an optimization to be made here, and it can be best observed with the transient response curves. So combining the lessons we just picked up in the prior set of slides on power factor and transient response, I'm going to now walk through how a simple motor starting scenario may play out. Here's what you may typically see for a three-phase induction motor in terms of its electrical characteristics. These curves represent a genericized across the line voltage starting. What you'll see on the left side of the plot is the very initial characteristics of first starting that motor. There is a high inrush current, also known as locked rotor current, shown by the green line. You'll note I don't place any numbers on this vertical axis, but the rules of thumb are around inrush current being 6 times the full load current output of the motor. Tracking that green line, it is when the motor reaches rated speed when the current draw finally reaches its normal level. The big reason for that high inrush current is because of the impact of power factor we talked about before, and that power factor shown in the magenta line here. When that motor is first getting started, so much of that electricity being consumed is to create magnetic fields or reactive power. When the motor is just starting, the power factor is quite low. So the current needs are quite high. That's why motors get so much attention in generator set sizing. Next, let's look at the red line for available motor torque and the blue line for the demanded load torque. Following these solid lines throughout the speed range of the motor, the available torque being greater than the demanded torque means that we should be starting this motor without an issue. Checking against a locked rotor KVA curve of an alternator data sheet should allow you to confidently check against this crucial phase at the beginning of motor starting. So how do we best specify for this phenomenon? I'll offer some good examples for recommended specification language to help drive the right conversations between you and the generator set manufacturer. So first, be realistic with the maximum allowed voltage dip against the particular loads being applied. It may be an interesting point of comparison to specify a minimum voltage dip to the entire generator set nameplate rating, but that is not realistic and not going to happen for almost every application. I highly encourage you to clarify your specifications and double check to make sure that they call out transient response requirements to the loads being served, namely the largest load step in the system design. The loads, after all, should be driving the voltage dip requirements in the first place. So the specification language should reflect that. Secondly, with regard to motor starting recovery specifications, when you cite a recovery voltage to best fit your needs, I encourage you to level set the requirements of voltage recovery by referring to NEMA NG1. This can be confirmed by the manufacturer with an alternator data sheet. And if that is not available via an actual test demonstrating the field forcing capability of the alternator proposed. So jumping back and taking another look at our motor load response plot that we just showed, let's take a slightly deeper look. As I mentioned, the red solid line represents the available motor torque of the alternator. This value has one complicating factor though, and that is that this solid red line is assuming constant speed of the generator set throughout this process. We mentioned earlier that an engine-driven generator set is not nearly as strong as the utility, and when a motor load is applied to that generator set, a transient response, like what we mentioned earlier with the frequency and voltage dipping down, that will have an impact on the available motor torque. So in this example, let's show you what may happen due to the generator set getting bogged down by that load step with the dashed red line I just added, reflecting the ultimate impact of that voltage dip or voltage roll off. If the available motor torque is ever lower than the torque demanded, as shown at the very beginning here, that motor is probably not going to start. That is one of the big pitfalls of solely relying on an alternator data sheet for calculating the anticipated locked rotor KVA. It doesn't show the impact of the engine or the prime mover's dip in speed. So again, the solid red line assumes constant speed with an ideal prime mover or engine. The dashed line takes into account a realistically sized engine and how it may respond and impact the available torque. Realistically, though, I mentioned earlier that it's this is a across the line starting, and it's probably not going to be the case always. And also, high inertia versus low inertia loads may come into play, and there are different forms of starting aids. So that can greatly alleviate the issue of the torque that's demanded by the loads. And I reflect that here with the dashed blue lines. So in this case, what we have here is we're returned to a situation where red is above the blue line, the available motor torque is above the demanded load torque, and we're back to being in a good situation. The ability of a generator set to appropriately respond to a large motor load is also a system requirement on the entire generator set, not just a component requirement of only the alternator. Solely relying on calculated voltage dip of the alternator alone may paint an incomplete picture. So how can we know for certain that the generator set will be able to accommodate the required load to start such a motor? And well, that's the beauty of generator set sizing software. This software is loaded up with tons of generator set performance data to most closely model how the engine and alternator will respond to your particular loads. Perhaps the example above paints an exaggerated picture. It is a theoretical case study here, but it's a situation that you don't want to have been caught unawares. Sizing software for the generator set solution is how you get that reassurance. So To close on this topic of motor starting recovery specifications, we discussed the impact of importance of how the engine or prime mover complicates an otherwise simple interpretation of an alternator locked rotor KVA capability curve. With that phenomena of voltage roll-off due to the engine or prime mover decreasing speed and thus diminishing voltage and torque availability. Specifications should also put the onus on the manufacturer to demonstrate testing the generator set as a complete system, such as with prototype test report, and also ask the generator set performance expectations against your load profile with sizing software meant to model the complete generator set. I know that I only offered a relatively brief primer on this, and if you're like me, you'd like to read it on your own time and pace, I have a slew of white papers here that explain what I just went through in a lot more detail, and I definitely recommend them. Just to reinforce that last point, I'm going to launch one more poll here for you, I think. So question to you. The alternator shall accept which of these with a maximum voltage dip X%? So what is the best required language that we should be using here in our specifications? Yeah, I'll reiterate, if you have a requirement for maximum voltage dip response, a transient response requirement, I would assign that to the largest load step of the generator set in the power system. When I would call, for those of you who call out full generator set nameplate, if anything, I would just specify, can it even happen or not? But you don't even want to measure that. It's kind of like if I'm buying a minivan and I want to specify a 0 to 60 time under 4 seconds or something. It's cool to know, but it's not going to be necessary or practical. So to those of you who said C, yeah, that's the answer that I would use. It's the most practical. Now we are done with the heavy stuff, and we are on the fourth and final segment of this presentation. We just covered the high-level overview of how a generator set may respond to an individual load. Now we're going to put those individual loads into context with one another. Because in the real world, of course, we typically don't assign just one load per generator set. The ordering and the organization of loads can have a potentially big impact on the ultimate recommended size of the generator set. And in this next section, we'll cover some tips and key starting points for best optimization of those loads. So let's take into consideration the example I have on the screen. We have 2 steps now. I know it doesn't seem radically more complicated than before, but this is all we need to put the lesson into context. So let's say, for example, we have one 300 horsepower motor on one step and a purely resistive, simple base load of 100 kilowatts in another step. Starting with that base load, we apply the 300 horsepower motor, which translates to a peak kilowatt requirement of 489 kilowatts, just shy of 500 kilowatts. That's to accommodate the starting needs of that motor. Once that motor reaches full speed and the average load settles out or in around the 343 kilowatt range, that starting load of the motor is the most demanding portion of this load sequence, and putting that starting load on top of the existing load, the cumulative step kilowatt requirements are compounded. In this load case, we are at least looking at a 500 kilowatt generator set. You may recognize it's around similar load steps as the earlier examples. However, let's simply switch the order of these 2 steps. This time, we start with the hardest load on the generator set, the motor. And once we get past that inrush period and allow for the motor to settle to its rated speed, then we hit the next step with the 100 kilowatt load. Overlaying that second scenario in red over the original scenario in gray, you can see the peak requirements are below 400 kilowatts even. Through all the loads are the same. In this scenario, we might be opening the door to a different model of generator set, or perhaps a smaller alternator, perhaps. So just imagine when potentially dozens and dozens of loads over a variety of load steps are in play, there are plenty of opportunities to optimize the load sequence to minimize the generator set size and ultimately the cost. So one key takeaway from this otherwise simple scenario is to, of course, use load sequencing to your advantage as best as you can. A generator set is not as strong as the utility, and putting the hardest load requirements early on in the load sequencing can be a helpful tip. That said, I'm going to put a big asterisk or complication on that prior point that I just made. I said in the very start, engineers, that's why they pay us the big bucks, right? We're always working with differing requirements and optimizations. Not all loads have the luxury of being placed exactly where we want them to make a perfectly optimized load sequence. Further, we cannot assume all motors just need to be started once. That brings us to the conversation of required capacity against the loads per code requirements. And I'm going to do my best to quickly abbreviate the NEC, the National Electric Code, in one slide. So let's go ahead and get started. Ordered from the highest to the least crucial, Article 708 for critical operations power systems are loads or even entire facilities that are essential for national security, public health, quite impactful to society. And in Article 700 loads, those serve the protection of human life in the event of a blackout, providing means of egress for safe evacuation. Loads for fire suppression systems fall under this category. When it comes to the capacity of these loads, and more directly in the context of what I just covered regarding load sequencing, we need to assume that these loads must be served simultaneously at all times. So when it comes to certain loads, such as I'll just pick on the fire pump, for example, we cannot use the strategies we just highlighted on the prior slide due to its importance. We want to ensure, just in case things start out of planned sequence, that the life safety loads can still be started. So in other words, we need to plan for the worst, and we cannot simply rely on that tip we just covered for these very important loads. Looking at the third item in this table, next, we have Article 701 loads that are still legally required, but may not be as directly impactful to human life. These usually are loads that are in support of rescue workers or firefighters. The language regarding the capacity of generator sets for Article 701 loads is a little softer. As a result, it may mean having an early conversation with your AHJ. Ultimately, if assuming the sequence of your legally required loads bears little impact on the size of your generator set, then perhaps going with the most conservative approach may be a sound decision. Otherwise, this could be an AHJ conversation. And lastly, Article 702 loads are optional, but as we may know, there are certainly customers who have loads that are very important to them, such as powering refrigeration in a grocery store or data centers. These loads, however, if they are on one individual generator set, must be designed such that the lower priority loads must be dropped if necessary, such that the more crucial loads can be maintained. So as we take a step back on that exercise on load sequencing a motor among other loads, one key caveat is that those motors serving life safety loads, such as fire pumps, should be sized and sequenced as if it was not started ahead of other loads. We basically need to think pessimistically or conservatively to ensure there is plenty of capacity for starting such loads, even when it is out of the most ideal load sequencing order. So I'll leave you with this really well done white paper. So I did touch on fire pumps just a little bit. There's special caveats around fire pumps, even above and beyond what I mentioned. There's plenty. And so this white paper does a really good job of covering those details. So I'm hitting the home stretch here before I close out. I'm going to offer a quick set of tips here. And just to be mindful of time, I'm going to breeze through these and leave them for your reference. I'd rather have a little bit more time for Q&A. But when you get a copy of this slide deck, you should be able to reference these later. The goal of these tips here is to offer good starting points for those of you who are new to approaching sizing software, to kind of offer some key rules of thumb when it comes to specifying or how much wiggle room you should have for voltage dips and frequency dips. Of course, every load is unique. Some requirements are stricter, or some requirements can get away with more of a transient dip. With regards to fuel, I suggest if you are indifferent, put no preference in your sizing software, just so you can see for yourself how capable a gaseous generator set is in terms of transient response. Of course, you can always go back into the parameters in the project later when the fuel type gets ironed out. And then lastly, When it comes to reverse loads, such as accommodating elevators that happen to feed their power back to the utility, a generator set can, generally speaking, not accommodate more than 10% of its nameplate rating in terms of reverse loadings, or else you start running the risk of motoring the gen set. And also, one key pitfall of sizing software, I know it can sometimes be a challenge as a newcomer. If nothing happens, make sure you don't over constrain yourself with requirements. That could have been the challenge that you saw. But otherwise, we have some great power hours on that walk through engaging with our sizing software, which is also good for general use and even for other sizing softwares as well, that I couldn't recommend enough. So that brings me to my final point here. If you're ever stuck, that's why we're here. We have plenty of experts available for you to call upon, and we'd really like to be there for you. Sizing can feel sometimes more like an art than a science, and that's why your local application engineers are available to help you out. So in closing, I know we covered a whole bunch of content here, and I'm really excited to just to engage with you all in the Q&A. And I also, for your convenience, threw together a greatest hits list of all the references I cited throughout. So let's go ahead and get started.
Thank you, Mark, for the excellent presentation. In the meantime, we just want to remind you that Cummins provides product application engineer experts in all regions in the US and Canada, including the two guest panelists we have with us today. These Cummins application engineers are happy to help you by providing technical information, designing and specifying assistance in order to comply with local, regional, state, and national regulations. Our application engineers provide local in-house presentations and expert advice and are backed up directly with our factory team of product and code specialists, ensuring the best professional network is at your disposal. Cummins is your partner in professional continuing education through Power Hours, Lunch and Learns, and other continuing education programs. Before we wrap up today's Power Hour, let's jump into some of the questions. So we talked a lot about motor starting throughout today's presentation. And so Bob, I'm going to bring this question kind of your direction. Can you talk about some of the common motor starting methods that you see or commonly used in starting and load schemes?
Yeah, Mike, thanks for the question. I appreciate it. There's really kind of no such thing as a common motor starter or starting method. It really kind of depends on the application. So, we like to circle back and most of the times you hear us saying it's application specific. Mike, I think that's probably the best answer. It's really application specific. A lot of fractional horsepower motors, for example, across the line starting is fine. There's no problem with that. You also kind of want to mix and match, with variable frequency drives or reduced voltage starters or such. There's a certain mix of those types of things which can actually contribute to better performance from a gen set. Rather than being all variable frequency drives or all reduced voltage starters. So, without trying to cop out on this one and say, gee, what am I seeing? I think what we're seeing most prevalently is application-specific starting methods by designers and engineers based on best practices, and that would probably be my answer on that one.
Awesome. Thanks for the great input. So I'm going to jump there. Are a couple of questions that came up during today's presentation around kind of the order of operation for stepping on loads. And Dennis, I'd love to hear your thoughts, and Bob and Mark, of course, as well. There were questions asked about, hey, is it better to step the smaller loads on first, the bigger loads on first? And then there were actually some questions that addressed that from an NEC standpoint and said, hey, if your smaller loads are your Article 700 loads, how does that affect your starting scheme? Can one or more of the panelists weigh in on kind of starting recommendations and methodology for load sizes and how we set those on?
You want to wing that one, Bob, or shall I?
Well, I'll take the first part of it and then probably, give you a chance to swing the bat on the second part. Okay. That's kind of a mixed question. Let me start off with, the most prevalent load that I think that we all struggle with is the fire pump load. You talk about essential circuits and such, one of the most common questions I get with people that are using sizing software is, where do I put that fire pump load? Well, just keep in mind, that even our software is going to take that load and throw it, in the 15% voltage dip area where it needs to be by code. And so you're kind of going to end up, if you put that as the first load in your load steps, you're going to end up, with a much larger generator than you actually need in order to do the jobs. So how you and how you stage and step them, if you want to put it that way, is fairly important. As far as the Article 700 loads, I think the common approach that we see most often, Dennis, and you can pick it up from here, is the large loads. And the Article 700 loads, of course, we see those dedicated on transfer switches, within a distribution system. But we usually see the larger loads applied first to the genset. Dennis, what are you seeing out there?
I agree with that. That's generally what you see. The one thing that I have learned over the years is that if you have a large motor on as your first step, then your other motors will actually start better, because that instantaneous time that you put the smaller motors on, that larger motor is going to act as resisting slowing down. So it's going to be actually producing like a generator. But yeah, larger motors first, because that usually works out to be the best.
Really good commentary on around. I'm gonna keep us on for one more question, if that's all right with the panelists here. There are some questions asked about gas and diesel generator sets. And I think Mark did a pretty good job of walking us through. Here's where each one of them performs. There were some questions about the cost difference, but I think I want to just offer up an opportunity for any of the panelists to jump in here and talk about the way we see gas and diesel generator sets operating and serving, whether it's life safety loads or otherwise. What are you seeing? What are you seeing as commonly accepted? And what are you seeing as those common threads between diesel and gaseous generator sets?
That's a good question.
If you're looking at the cost factor on natural gas or gas generators versus diesel, usually the breaking point is either 150 or 200 kilowatts, depending on the manufacturer. Because once you get above 200 kilowatts or 150, depending on manufacturer again, you're going to have a diesel engine that's been gasified. So the engine itself is much more costly because there's less BTUs in gas than there is in diesel. So the breaking point is about there. Anything above that is going to be more expensive than natural gas. Anything below natural gas will generally be less expensive.
Yeah. And if I could, just for a bit, a lot of people ask me, what about gas? Well, and I say, well, where can I use gas? Anywhere you have gas, I guess. There's some more careful planning that we need to do when we're looking at a gas system than we would with the diesel, because diesel is traditionally more robust. But as Mark mentioned early in the presentation, Cummins is not short on gas power. And in some instances, gas is actually preferred in terms of, the accessibility to extended run times. This is why you see sometimes blended fuels or what's called biofuel as well. So, gas no longer is here and diesel is no longer there. It really kind of depends on the application. Some areas don't determine pipeline gas as a reliable source, so you have to be careful. You got to check with the utility and the AHJ when you're looking at life safety loads and you're looking at life safety systems. But don't forget natural gas. I mean, it is available. It's out there. Machines are getting better and better all the time. And Cummins plays in that market pretty well. So that's a great question, Mike. Thanks for coming at us.
Awesome. With that, we are going to go ahead and step out of our Q&A session. I first want to thank our panelists for joining us here today, and all of you for participating by engaging us through active questions and answers throughout today's session. In closing, watch out for 2 follow-up emails from us. The first will be provided shortly after this event with your certificate for 1 professional development hour for your participation here today. Within a few business days, keep an eye out for a second email with links to this video recording and a copy of the slide deck for your later reference. Immediately after the close of this event, you will see a brief survey. We ask that you please take the time to complete that survey. Your feedback is greatly appreciated. It helps us to improve this program for future events and participants like you. As always, consider visiting Cummins PowerSuite at powersuite.cummins.com for past webinar recordings, technical information, and sizing and specification development tools. I'd also like to remind you that Cummins is your partner in professional continuing education through Power Hours, and we offer a wealth of resources for you to reference on your own or subscribe to get information straight to your inbox. Recordings of previously conducted Power Hours are available for on-demand playback at your convenience at powersuite.cummins.com. Cummins also recently released a podcast called Brightest Bulbs. There you can learn about the latest innovations in energy and power, or find out what's in the works to build a sustainable energy future. You can go to cummins.com/podcasts, click the link in the presentation when you get your copy of the slide deck, or search Brightest Bulbs wherever you get your podcasts. Lastly, watch out for our next Cummins Power Hour, what to specify and why. I highly encourage you to check these out, most notably the information on our brand new line of transfer switches available on PowerSuite and in the Power Hour coming up shortly. Thank you for attending this Cummins Power Hour. We hope to see you next month for another exciting topic.